Okay, last mini lecture in this section, section 5.1. We're going to look at radioactive decay, and we're going to look at number 58 here. I'm just going to read it out loud. You can look in your book. It's on page 399. Let Q represent a mass of carbon-14 in grams, whose half-life is 5,730 years. So again, Q and 5,730. The quantity of carbon-14 present after T years is represented by this equation here. Okay, part A, it says to determine the initial quantity of carbon-14 that we have in this problem. Let's set T equal to 0. So if T equals 0, we'll have 0 over 5730 here. And anything to the 0th power is what? Anything to the 0th power is 1. So it would be 10 times 1, which means that we started with 10 grams of this carbon-14. Now, part B, determine the quantity present after 2,000 years. So we're going to now put in 2,000 for T. Okay, we can do this on our calculator now. Let's go ahead and do that. So we're going to have, let's clear all this. So we're going to start 10 times, I'm going to just say 0.5 here, to the, what is this, 2,000 divided by 5730. So even after 2,000 years, we still have 7.85 grams of this carbon-14. This stuff does not decay very fast, does it? Does not decay very fast. Okay, now it says part C. Sketch the graph of this function over interval t equals 0 to 10,000. So let's go ahead and do some graphing on this. I'm going to clear all these. I'm just clearing them all. Okay, so let's type this bad boy in here. We got 10. Whoops, what did I just do there? 10 to the 0.5 to the x over 5730. That's what we're going to have. Now it says we want to have x from 0 to 10,000. So let's make sure our x minimum is 0. Our maximum is 10,000. Let's change each of these tick marks to say 1,000. And our max, let's keep the max there because we started with 10. And let's see how close it gets to 0 after 10,000 years. Let's go ahead and graph this. Okay, so that's our graph. So after 10,000 years, we still got a fair amount of it in there. We still got a fair amount. Let's look at a table of that. Oh, well, let's actually just go back to the graph and let's trace it here. So I'm going to keep going. And let's see. So after 10,000 years, gosh, we still got almost 3 grams of carbon-14 left. So that's why, there's such a big deal. I'm sure you guys have heard about Yucca Mountain before. Maybe one of your parents have worked on that job site or helped to maybe design that job site. So you can see what happens is we have this, radioactive waste. And the half-life of some of this radioactive waste is on the order of years. It could be like on the order of 5,000 years. And you can't do anything with this waste except just let it sit and hope that it decays, over time and then becomes less radioactive. And you can see like in this kind of problem, even if you waited 10,000 years, you still have, almost 30% of that radioactive waste left sitting around. So that stuff needs to be really safe, and it can't, it has to be in a place where it can be contained very well. And that was that's the big sticking point about using, nuclear power and having radioactive waste is that you have to have some place where it can sit for a very, very, very long time without being disturbed and without getting spilled or anything like that. Because if it spills, that's not going to go away anytime soon.